Hi guys, here are last two questions of miscellaneous section NBHM PhD 2019. We'll start with the last question. Okay, let's read out the question first. A portion of wooden cube is sawed off at each vertex so that a small equilateral triangle is formed at each corner with vertices on the edge of the cube. Okay, so let's first of all draw the cube itself. So what we do is, this is a wooden cube. It's there is inside and then there is material inside also. Okay, so what we do is basically we pick out a pyramid kind of portion from here. Okay, at each vertex. So let's consider this first vertex A. So what we chunk off a pyramid portion. Okay, so what will happen, it on the edge it will be like small equilateral triangles like this, and on this one it will be like this. And if we consider again on the back side of the face, there will be another an equilateral triangle will be forming. If you consider this vertex, an equilateral triangle will from here, an equilateral triangle from here, and another equilateral triangle will from here. Okay, so basically for each side we have 2 points, right? And what we do is basically we consider for each edge we consider two points on edges. Okay, like 2 points, and then what do? We join them on their faces. Okay, so that part is cut out. Okay, so after this let's read the question. So the 24 vertices, so of course since there are 12 edges, there will, for each edge we have two vertices of the equilateral triangle, so there will be 24 faces, right? So for these 24 vertices of the new objects are all connected to each other, okay, by straight lines. So what we do after this is, this I'm considering these only. Of course we need to consider all of them. So what we do, we connect all of them. Okay, so this is connected by straight lines, and this is connected to this one is connected to this, like this. So we can see that some of it are in the interior if we join this one and with this one, but if we join this one with this one, it will lie on the upper face, right? So it will not be inside the cube, inside the wooden cube, right, after it has been cut out, of course. So of course, so the question is as follows: how many of these lines, with the exception of course at the end points, of course at the end points they cannot be inside the interior point, so how many of these lines lie entirely in the interior of the original cube? Okay, so basically we want to compute the number of lines which will lie inside the cube. Okay, so now first of all what we do is we first fix a particular edge. Okay, so we fix this one. Okay, so consider 2 points. Okay, so note that if we join these two with any with this edge or this edge with this edge, or with this, basically with the edges which are in the face of this particular line, the particular edge lies, they will be inside that, they will be on the edge, right? So if we connect this with this or this with this, we will not get any interior lines, right? So what we need to do, we need to connect this, let's call it AB, with this one, this one, this one, this one, 4 of them, and this one is the last one, right? So there are 5, so in total 12 edge. A cannot connect with itself, right? So and then 6 from 2 faces we will have 6, which if we connect then we have on the edge, and there will be 5 when we will get our interior things, right? So how many of them will be there? So there are in total how many edges? 12 edges, and for each edge we have we got 5 many lines. many interior lines. Okay, now note that if we connect these two, and when we consider this edge, again we will count this one with the first one, right? So for we are counting it twice, so we need to divide 2. But okay, fine. Now there is a consideration. Now just focus on two particular edges. Let's suppose AB and GH. Okay, so this. Now how many ways can we join these two? So this can join with this can join with this is a one way. Then there is something, this joins with this and this joins with this is another way, right? So there will be how many possibilities? So this one is there, right? Okay, so there will be how many number of, for I mean, if we consider two edges, there will be exactly 4 interior lines, right? So which are basically this one, and then this one, and then this and this, the four lines. So for each pair we have 4, right? So we are multiplying these events what we are talking, these are happening independently, right? So we're multiplying it. So and this consideration exhausts all the possibilities, so which implies that this is in these many ways there will be, I mean, the lines will be inside the lie entirely in the interior of the original cube, right? So the answer will be what? 12. So it will be 120, right? Okay, so now suppose if you are asked in the question that how many of these lines will be on the face, so what we will do, the same thing we'll do, like for each there will be 12 cubes, 12 edges, right? Then instead of 5 we will write 6, because there are 6, if we can connect 6, I mean, for each edge we can connect with 6 edges, so that it lies on the on the face, right? Okay, so and then again, if we consider any two particular edges, there are 4, these 4 will be there, right? So 4 will be on the face. Okay, again for this we are considering this, when we'll consider this edge we'll be counting it twice, so we divide by 4. Now the answer will be what? 144. So for the edge, so how many of them will be there? 144 will lie on the edge and 120 will lie on the inside it, I mean in the interior, right? Okay, so now we move on to our next question. The question is as follows: we are given with a set X, and V is the real vector space of real valued functions defined on X with pointwise addition and scalar multiplication as operations. Okay, then in addition we are given that if F belongs to the vector space, then F square belongs to the vector space, and mod of F also belongs to V. Okay, so we are asked which of the following statements are true. Okay, so now if Fg are V, we are asked to find out if F times G is inside V or not. Okay, now note that Fg, it can be written as what? F plus G square minus F minus G square, isn't it, by 4. Okay, now since V is a vector space, and we are taking Fg inside V, F plus G and F minus G, both of them are in V, right? And by it is given that F square is also in V, right? So it implies F plus G, this and this, these are also V. Now F times G is a linear combination of these two, so F times G also belongs to V, right? Okay, now this option is of course true. Then if F belongs to V, then we are given that F square belongs to V, right? Now product of these two will be what? F cube, right? So but we showed in first option that F times G belongs to V. This would imply that F cube belongs to V, right? In particular, we can show that F to the power n for any power of n is inside V. We use by induction. Of course, F belongs to V, and now F to the power n can be written as F to the n minus 1 times F. Now since by induction hypothesis, F to the this belongs to V and F belongs to V, and product of these two also belongs to V, right? Now let's consider the B option. This is also not that difficult, because we can write maximum of fg as in terms of modulus functions, right, which is f plus g by 2 plus f minus g by 2. It is very instructive to verify these two are equal by taking cases. Okay, now since we are given that mod f belongs to v and fg are in also v, so it is a linear combination of f plus g mod and f minus g mod, so this also belongs to v, right? So option B and C, both of them are correct.